Assalamualaikum warahmatullahi wabarakatuh. This video is presented for project of the subject BFC15003 calculus with our lecturer Dr. Susilawati binti Ismail. Meet our team of 5 members for this project, which is Misha anak Jody Imau CF240117, Brady Jayan anak Daniel Ritchie CF240187, Melissa Sarafina CF240007, Hazlinda Fazrin anak Frankie CF240380, Nur Afini binti Branse CF240418, which is myself. Calculus is a vital mathematical tool with broad application in engineering and data analysis. In our project, we demonstrate how differentiation and integration are used to solve real-world problems in civil and environmental engineering. We analyze traffic flow to help optimize infrastructure and reduce congestion, examine river water level patterns to support flood mitigation, and evaluated fracture energy in materials for safer structural design. This example highlights how calculus enabled us to model, understand, and improve complex systems that are critical to enhancing safety and efficiency.
My name is Brady Jayan. My metric number is CF240187. For problem 1, we need to plot the graph, describe what we observe in the graph, and find the rate of change, and identify and interpret critical maximum and minimum point from first derivative, and compute the second derivative to measure acceleration and interpret the result. As can be seen, our result has been plotted in graph and have been interpreted by table. So the volume trend that we got is from 15 to 30, 30 to 45, and 45 to 60. The volume trend decrease, but from 60 to 75, the volume trend increase. After that, the 75 and 90, the volume trend decrease, and 90 to 120, the volume trend is increase. Interval, the rate of change. At the first column, we got negative 1.07 rate of change from 15 to 30. While 30 to 45, we got negative 2.13. 45 to 60, we got negative 2.40. And 60 to 75, we got positive 4.33. And 75 to 90, we got negative 1.2. 90 to 105, we got 1.6. And 105 to 120, we got 3.13. The highest value in the interval around 60 to 90 minutes. Then the lowest value in the interval around 45 to 75 minutes. Then the graph for average speed was time. From 15 to 60, the interval time, the volume trend that we got is decreased. While 60 to 75 is increased, 75 to 90 is decreased, then the 60 to 120 is increased. The rate of change that we got for the average speed was time. From interval 15 to 30, we got negative 0.11. 30 to 45, we got negative 0.08. From 45 to 60, we got negative 0.11. From 60 to 75, we got 0.04. And from 75 to 90, we got negative 0.07. And for 90 to 105, we got 0.16. While from 105 to 120, we got 0.29. The highest value in the interval we will get at 60 to 90 minutes, and the lowest value in the interval we got around 45 to 75 minutes.
From the data time and volume, we can get the cumulative volume data column, where the volume for the first 50 minutes is remain the same, which is 260, and the next 50 minutes, which is 30, is we need to plus the two value of the volume. For example, 260 plus with 244, and then we got 504. Now, the rate of change we got for the cumulative volume, the first interval, which is 15 to 30, we got 16.27. 30.45 is 14.30. 45.60 is 11.73. 60 to 75 is 16.07. 75 to 90 is 14.87. 90 to 105 is 16.47. And the last one is 105 to 120 is 19.60.
Hello, my name is Misha Anajoni Mau, and my matrix number is CF240117, and I'm going to present about the problem 2. Okay. Firstly, we had to collect and tabulate the water level data from website, the official web of public info Banjir for 7 days. Then our group analyze for Selangor State, and we chose Hulu Selangor District. Alright, then we have to select the 5 stations, which are Sungai Liam, Sungai Serendah, Sungai Batangkali, Sungai Guntong, and Sungai Keling. Then, in this slide shows the graph plotted by the collected water level data. Sungai Liang marked in dark blue, Sungai Serendah in orange, Sungai Batangkali represented in grey, Sungai Guntong shown in yellow, and lastly Sungai Keling marked in light blue. Overall, all rivers demonstrate stable water level trends with only minor fluctuations. Then the most noticeable change is seen in Sungai Guntong around mid-June, possibly due to localized rainfall or upstream activities. Next, I want to describe the observation from the graph, then identify any increases, decreases, or pattern over time, then explain what the changes mean in the context of river water level. So for this presentation, I chose only one station to describe. I chose Sungai Liam, and the Sungai Liam have decreased around 10 June until 14 June, increased slightly in 15 June until 16 June, and decreased again on 17 June. The explanation for the changes, there might be minor runoff or short-term rainfall.
In this slide, I would like to explain how to compute the first derivative dH over dt, where h is the water level and t is time. Okay, it's already show that the graph of water level and the date for 7 days to get 7 different result of water level for Sungai Liam. And first step is first derivative, the rate of change of water level and Vs time. It's already shown the formula given. Okay, how to calculate is we take the water level from 10 June minus to water level from 11 June. Like, for example, 32.83, minus 32.61 over divided by 1, and we got negative 0.22 meter per day. Same goes to others step lah. After that, we need to repeat this the same the same step of calculation with others sungai. Okay, in this slide, I would like to explain how to identify the critical points, maximum and minimum values, and explain their significance. Okay, first for location at Sungai Liam, uh, maximum value is 32.83, while minimum is 32.54. Sungai Liam began the time at its peak and progressively declined to its lowest position in the middle of it. According to this pattern, the river was gradually recovering to its typical level throughout the week after a high water event, such as recent rainfall, that took place immediately before or on June 10. Second is Sungai Serenda. Maximum is 34.44. Minimum is 32.54. For Sungai Liam and Sungai Serenda peaked early in the observation period and subsequently started to decline. This suggests that these two rivers may share a watershed or have been impacted by the same meteorological phenomenon. The maximum risk overflow for this river during the week is represented by the peak on the 10th. Okay, third is water level at Sungai Batangkali. Maximum is 32.55 and 32.17. It shows a trend nearly identical to that of Sungai Liam and Sungai Serenda, with a peak water level of 32.55 on June 10 and a minimum of 32.17 on both June 13 and 14. This pattern of an early peak followed by a midweek dip suggests and all three rivers were likely affected by a common regional event, such as heavy rainfall at the start of the period, reinforcing the interpretation of a shared hydrological influence across their catchment areas. And fourth is at Sungai Guntong. Maximum 15.35 and minimum 14.34. Sungai Guntong show a distinct and notable pattern, with its lowest water level recorded at 14.24 on June 13, possibly indicating a period of dry weather. However, it experienced a sharp which is more than a full unit higher than any other day in the period. This sudden peak is highly significant and may have been caused by a localized intense downpour near the monitoring station or a sudden release of water from an upstream, such as a dam, marking it as an anomaly compared to the more stable trend observed in the other rivers. Lastly, water level at Sungai Kerling, which maximum value is 44.97 and minimum value is 44.23. Sungai Kerling display a trend opposite to the first three rivers, starting at the lowest point on 10 June and showing a gradual but steady rise, peaking at both 15 and 16 June. This consistent increase suggests the Sungai Kerling is likely located in a different catchment area and was not influenced by the same factors that caused elevated levels in the other rivers earlier in the period. The continued rise toward value in the entire dataset raises concern about potential flood rise risk in the specific region and highlights the need for ongoing monitoring. Okay, lastly, how to compute the second derivative dh square over dt square and interpret the result. Okay, for water level at Sungai Liam, the second derivative acceleration or declaration of water level changes. It's already shown the given formula in this slide. Okay, how to calculate is negative 0.05 minus in bracket negative 0.32 divide by 1, and we got 0.17 meter per day. How to get negative 0.05 is from the result um, before calculation for first derivative. And okay, after that, all the result calculation from first derivative, we take and calculate for the second derivative. Okay, after that we got the result of the second derivative calculation. And that's all. We need to repeat this calculation for each river of water level.
So my name is Melissa. I will present about problem 3 for method 1. So this is the graph that we got for our data. So our data max point is from 1 to 153. For method 1, y equal to negative 8e minus 06x power of 2 plus 0.0039x minus 0.0021 integrate negative 8e minus 06x power of 2 plus 0.039x minus 0.0021x dx equal to negative 8e minus 0.6x power of 2. So divide by 2 plus 0.039x divide by 1 minus 0.0021x plus c. So we will get negative 0.18x power of 2 plus 0.039x plus 0.0021 plus c. So we will write x equal to 0 to x point equal to 0.414. So this method is for manually calculation. So for the manual calculation, we got the area under the curve is equal to negative 0.01557 units. So for problem 3, method 2, so as we see here, this is the data that we got on the third column. So for method 2, by using formula, which is we need to calculate it in Excel by using formula equal to 1 over 2 times B3 minus B2 times A3 plus A2. So the manually calculated fracture energy is 0.039836153 kN per millimeter. So the comparison of method, polynomial, trend line, and integration pressure friction energy equal to 0.039836153 kilonewton per millimeter, and for secondly manual calculation, the friction energy equal to 0.01557 kilonewton per millimeter.
From this project, we demonstrate how calculus is essential in solving real-world civil engineering problems. We use differentiation to analyze changes in traffic flow and river water levels, which help us understand how this system behave over time. Integration was applied to calculate the fracture energy of materials, an important factor in structural safety. Overall, our project showed that calculus is not just theoretical, it's a practical tool that enables precise data driven solution in engineering. That's all from us. Thank you.